And let's go back to page 115. So last week we finished chapter 5, the title of which is Reactor Kinetics. So if you remember the title of this course, Nuclear Reactor Kinetics and Control, then you may understand how important this chapter 5 is. So previously, last semester, we basically studied the neutron distribution in space while ignoring their time dependency. In other words, we only focused on the distribution or the density of a neutron, the distribution of a neutron density in space, while ignoring or only focusing on the steady state condition, steady state neutron distribution. That means we do not have any time dependency in neutron density distribution. But of course, in chapter 5, it is what's called as point kinetics. So by the word point, it means that we are not going to focus on the space dependency. So only focus on their time dependency. So that's what we studied in chapter 5. So of course, in section 5.2, we started from neutron balance equation. And you may see here that the neutron density is now expressed as only as a function of time. We do not focus on their space dependency, the space dependency, or we do not focus on the energy dependency of a neutron density distribution. So it is simply NT. And then we gradually try to establish the neutron balance equations. So once again, we started from infinite medium. So by the word infinite medium, we ignore the space dependency. Non-multiplying system. So of course, by the word non-multiplying, we ignore the fission neutrons. And then infinite medium multiplying systems, and then after that finite multiplying systems. Now here we include not only the space, not exactly space dependency, but we at least recognize that we are going to deal with the neutron density distribution for a finite reactor. So how can you do that? So by introducing this capital gamma factor, which this capital gamma give us how we express the leakage term. So neutrons disappear by absorption, or by leakage. And to simplify the expression of the leakage term in a more simplified way, we introduced this gamma factor. And by using that, the equations that was developed for infinite medium can be, so what we realized is that the equations derived in infinite medium, which can be shown in equation 5.12. This can be also applicable to finite medium with a very similar form. So this is what we can see in equation 5.22. So instead of k infinity, now k is introduced. So here k is simply k infinity multiplied with non-leakage factor, non-leakage probability. And also L is given as the L infinity multiplied with non-leakage probability. So equation 5.12 in our previous page. So equation 5.12 is applicable to infinite medium, while equation 5.22 here, 5.22 is applicable to finite medium. So to derive this equation 5.22, we simply introduced the capital gamma factor, and with the assumption that the leakage term, the number of neutrons, so in our previous page here, so the basic assumption that we applied was that the number of neutrons that leak out of the system is proportional to the number of neutrons observed in the system. Because if more neutrons are observed, that means there would be much stronger neutron flux. Then in such cases, there would be much more neutrons will leak out of the system. So that is why we introduced this factor capital gamma. So by utilizing this capital gamma factor, so here we arrived at this equation 5.22. So now this equation is applicable to a finite nuclear reactor. So based on this, what we realized is that the NT changes as, so the change of NT, neutron density, is strongly dependent on this K, the multiplication factor. So after that, these are the solutions of neutron density. The first one is when, so this is the case when K is, let's see. So first, we solve the solution for the case when we do not have an external source. And second, so first, see, so first, when we do not have any external source. In that case, the solution is pretty simple. The second one is when the case when we have a time-independent source. In other words, constant neutron source. So by the word time-independent, ST is given as S0. It is a constant neutron source. So in that case, we needed to divide the cases into three cases. The first one is when K is bigger than 1. So when K is bigger than 1, then what we realize that neutron density will infinitely increase, of course. For a subcritical system, when K is smaller than 1, then NT is just like this. And what we realize is that when K is smaller than 1, the subcritical case, and if we have some constant external source, then we are going to have some time-independent neutron density. So that means if the neutron density NT has time-independent solution, that means if the neutron density maintains some kind of stability, not stability, if it has some stable density, some stable value that does not change over time. So a kind of a steady, steady-state solution. So there are two cases. The first one is in our previous section, previous case. If we do not have any external source, then if k equals 1, then we are going to have, here, we are going to have a steady-state solution for neutron density. If we have external source, then this is the case. When k is smaller than 1, that means for a subcritical reactor with external source, will have eventually time-independent steady-state solution for neutron density. So there are only two cases of having such time-independent solutions. And this is the case when k equals 1. So when k equals 1, then NT will eventually becomes S0T. So that means neutron density will linearly increase. So in our previous page, the neutron density will linearly increase. So here I also told you that in a nuclear power plant, the way the nuclear operators decide whether the criticality is achieved or not, so they usually monitor whether neutron density is linearly increasing or not. So when they really confirm that the neutron density linearly increases with a constantly increasing rate, then that is the time operators are able to declare the criticality of the reactor. So after first achieving the criticality, they gradually withdraw control rods to increase the reactor power. So after that, so far we have not considered the delayed neutrons. This is the solution for when we only consider the prompt neutrons. And this is these are how we include the delayed neutrons in our neutron balance equations. So there are some important properties of delayed neutrons. In case of uranium-235, we only have 0.65% of delayed neutrons. That means 99.35% of neutrons contributing to fission reaction would be prompt neutrons. Only a very small fraction of neutrons that contribute to fission reaction are delayed neutrons. And of course, this delayed neutron significantly contribute the controllability of a nuclear reactor. So by including the delayed neutrons, we developed the kinetic equations. So the change of neutron density is given by, so the plus part are external source, so prompt neutrons and delayed neutrons. And minus parts will be absorption and leakage. And also we need to, so for each precursors of delayed neutrons, that means for the fission neutron emitting fission fragments, so the concentration of such precursors can be described with this production rate minus the decay rate of the precursor. And we have 6 groups. Of course, there are hundreds of such precursors, but we usually divide those precursors into 6 groups based on their half-lives. So we have a simultaneous equation, one for neutron balance equation and 6 for the concentration or the concentration of precursors. And of course, we are able to calculate their steady state solution. And here we introduced reactivity. So reactivity is defined as k minus 1 over k. And by introducing this reactivity, now the simultaneous differential equations are now rewritten in terms of reactivity and this capital lambda prompt generation time. And how can you solve this? So, of course, these are something that we could observe, eventually solve the equation. But how can you? So, we basically assume that the neutron density here, this NT, and all CITs have this form of exponential function. And then we will be able to it seems that we lost the connection. 자, 들리나요? 네, 다시 이어진 듯 하니 계속 진행을 하겠습니다. So, so by assuming NT has this exponential function with this parameter omega, and also CIT also has this exponential function with the same parameter omega. And now we are able to solve the differential equations, the simultaneous differential equations. And what was found is that we have, so in that case, we are able to write, so eventually what is important is to find this omega given the reactivity. So reactivity is usually controlled with control laws or some chemical chain like boric acid. And for a given reactivity, so in the left hand side is the amount of reactivity given to the reactor. And the right-hand side, eventually we would like to find out the solutions for omega. Of course, as you can see in this somewhat complicated form of the right-hand side with respect to omega, the omega cannot be expressed explicitly. That means we are not able to find or rewrite this equation 5.53 in the form of omega equals something. So omega need to be found only in numerical ways. So numerical solutions will be found. And by observing equation 5.3, here the right-hand side is written in f omega. And what we realize is that there are 1, 2, 3, 4, 5, 6, and 7 omegas that satisfy this equation 5.53 for a given value of reactivity. So we are going to have 7 solutions for omega. So we are going to arrange the 7 solutions. First, we are going to write the 7 solutions as omega 1 to omega 7. And we are going to rearrange the omegas so that omega 1 has the biggest value and omega 7 has the smallest value. And then in that case, NT will be given as the sum of all exponential function, exponential omega it. And of course, the solution will be dominated by omega 1, the omega with the biggest value. And in fact, NT is approximated as with the first omega, the omega 1. So as time gradually increases, so only in the time, when time t is very small, so if we go back one page, then, so if omega is bigger than 0, you will be able to see that the neutron density increases almost exponentially. And this exponential part will be, so after time has passed for some amount of time, has passed, then as omega increases, time increases, gradually the function follows exponential omega 1t. But only in the time, when time is the time elapsed is very small. So in other words, only in the time, then the exact solution should be found by considering all 7 omegas. So as time gradually increases, then eventually the solution will follow exponential omega 1t, but to describe their early behavior, so just like the one shown here, like the prompt, if we want to describe the prompt jump, then we all need the 7 omegas. But eventually, as time passes by, then eventually the solution will gradually follow the omega 1t form. So the remaining term, as you can see, the remaining term rapidly die away. That means they are alive early in the time. In early behavior, they are alive, but as time passes by, the terms gradually lose their contribution, and only we are going to have this asymptotic solution. So mainly the NT is dominated by omega 1, 2. So the reactor period is usually determined by the inverse of omega 1. And also we have this and the behavior. This prompt jump is also an important behavior that need to be clearly described. And also when the rho, the reactivity equals the beta, the fraction of delayed neutrons. So in that case, see. So when low, the reactivity becomes or be greater than, equal to or greater than, or when the reactivity equals the beta, that is the condition called the prompt criticality. So in that case, the what is it? The chain reaction does not depend on chain reactions do not depend on the delayed neutrons anymore. That means with only prompt neutrons, the chain reactions can be sustained. That means that is the same effect that we do not have any delayed neutrons. So that is the case when we considered in our previous sections like section 5.2 and 5.3. So that is the case when the neutron density exponentially increases. And also because the L is very small value, so this exponential increase is the neutron density suddenly increases in a very short time. So it is very important that the nuclear reactor or reactivity should be maintained far less than this prompt critical state. And therefore, how close when we insert or when we withdraw reactivity, the magnitude of reactivity is usually described with how close the inserted reactivity is close to beta value. So the ratio of reactivity over beta value is given as this unit of dollars. So $1 means the reactivity is the same with the beta value. So $1 means prompt critical state. And if the reactivity is like 10% of beta value, in that case, it is called as $0.1 or 10 cents. So this dollar or cents unit is also used to describe the reactivity. So I also emphasized the importance of understanding figure 5.4, reactivity versus reactor period. And you also need to understand this graph with the, the explanations in pages 130 and 131. So the first one, so this is the case for a given capital lambda value prompt generation time. It gives us the reactor period for a specific reactivity value. If the reactivity is 0.002, then the prompt generation time do not have a significant contribution to reactor period time, and reactor period will be approximately between 10 seconds to 100 seconds. So that means the growth, even if we provide the positive reactivity, the increase or the change of neutron density follows exponential over t over 10 seconds. So that means if the reactor period is 10 seconds, then if we maintain such that reactivity for 10 seconds, then the reactor power will increase to exponential 10 seconds over reactor period. So the neutron density will increase like approximately 2.7 times with the time interval 10 seconds. So that's the very basic thing of reactivity, the reactor period. And when the reactivity is very small, that is when this is the area where the reactivity is very small, or these parts. So in this case, when reactivity is very small, then we are able to do some approximation for this. So in the case omega 1, if omega 1 is very small compared to lambda I, here, if omega is very small compared to lambda I, then this omega can be ignored. Then we are easily, so if we ignore the first omega term, then this would be the equation for that. So now it is very easy for us to find the solution for omega. So it is easy for us to find the one solution for omega. So that is given as omega divided by the term inside of this parenthesis. And of course, omega 1 would be, the reactor period will be the inverse of omega 1. So that is given here in 5.57. And the first special case is above prompt critical. So above prompt critical, also the equation can be easily simplified. So in that case, omega actually dominates, and omega will be much bigger than lambda i's. So lambda i's can be ignored in such cases. Then the omega here and the omega outside of a parenthesis can be cancelled out. So in that case, this omega is only multiplied to prompt generation time. So the equation, the form of equation is now given as given here. Omega equals, so the second term will be reduced to beta. So this is the how. So omega 1 can be omega can be given. As you can see here, omega 1 can be given in an explicit form. That is, we are able to find omega 1 in omega 1 equals something in this form, instead of finding omega 1 with numerical calculations. So when above prompt critical, the reactor period is given like this. Prompt jump approximation is the one. So previously I told you that to exactly describe this part, so in a very short time, so in this case the time span is less than 0.1 second. In a very short time, so this prompt jump is usually resulted by the prompt neutrons. So their response is very, how I can say, their response is very fast. In almost less than 0.01 second. Because prompt generation time is such a short number, such a short time. So, so I also told you that to exactly describe this prompt jump part, we first thing, one thing is to find all the omega 1s, all the omegas from omega 1 to omega 7. And if we exactly apply the equation, then we will be able to find this prompt jump behavior. But the amount of prompt jump can be easily approximated. So in that case, it is not an assumption, but with the property that Ci, this is Ci, do not significantly change. So in a steady state condition, Ci will be determined as in equation 5.59. And then even if we provide some positive or negative reactivity, their concentration, this precursor concentration, will not significantly change for a very short time period, like 0.1 second. Their change will not be that significant. So they can be assumed as a constant during that short time period. So with this is the case. So this is the case of a rod drop. So basically, the reactivity would be a negative value. We use this absolute value to indicate that only the absolute value part, or only the magnitude of the negative value will be used here. So with this, what we are able to find is a new, so at the level of neutron density after prompt jump compared to its steady state value. So what it means is that, so of course in this case, this is the case of a rod drop. So, of course, N1 will be smaller than N0 because we inserted negative reactivity. So if we go back one page, then of course it is applicable to this curve because we inserted a negative reactivity. So this is the level, this is the value of N1 compared to N0, the previous steady state value. So previously, the neutron density was maintained with the steady state value, and all of a sudden, at time 0, we inserted negative reactivity with the magnitude of minus 0.1 beta. So previously, I told you that this can be also, this amount of reactivity can be set as $0.1 or 10 cents of reactivity. So by providing $0.1 magnitude, $0.1 reactivity, so in a very short time, suddenly the neutron density decreases and eventually, here, eventually it maintains some steady state value before the precursor concentration changes. So in this case, with the equation, so this value, the issue is how can we calculate this value? So what we can see is it is slightly bigger than 0.9. The exact value would be, in this case, 0.1 beta plus 1 beta. And in the numerator, we have just 1 beta. So the overall N1 is going to be 1 over 1.1. That is approximately, of course, 0.9. So with the equation 5.62, we will be able to calculate the amount of prompt jump after load drop or after sudden increase in some positive sudden insertion of positive reactivity. And source jerk will be almost the same with the load drop because we are going to withdraw the neutron source in a subcritical reactor. That is the same with the effect would be same with inserting the control rod. Both will provide a negative reactivity to the reactor. So it is called as point kinetics. And of course, this understanding point kinetics is very important in understanding reactor, the overall reactor kinetics. Of course, later so in chapter 5, we have not considered the so-called feedback effect. So with the equations, so when we inserted some positive reactivity, first you will be able to see some prompt jump here. And then after prompt jump, the neutron density will, in fact, will increase exponentially. And but that is the case when we do not consider the fact that heat, after the increase in neutron density, there will be more fission reactions. More fission will also means that more heat will be generated from the reactor. And that heat will gradually increase the temperature of the nuclear fuel and also temperature of the coolant. And that increased temperature will provide negative reactivity to the reactor. So that is called as so that uh, inserted or due to the increased temperature, the negative reactivity will be provided to the reactor. So that is a kind of feedback effect. So that by increasing the power, but first by providing the positive reactivity, so eventually uh, negative reactivity will be naturally inserted to the reactor. So this negative reactivity feedback is given. In the opposite case, when we provide negative reactivity, so then less power will be generated. That means that the temperature of the fuel and coolant will decrease if sufficient power was generated in a steady state condition. Then their temperature will gradually decrease. And this decreased temperature will have the effect of increasing the power. So by providing negative reactivity, the positive reactivity feedback will be given. So just like that, if we consider such a feedback effect, then of course the change of neutron density over time will become more complicated than this simple exponential form. So that will be considered in our coming chapters in section chapter 8, 9, basically 8 and 9. And such feedback effect will induce some short-term change in neutron density. Of course, after that, we are going to, so this is a kind of a short-term effect. And after that, we are going to also consider some mid-term effect or mid-term treatment or management of reactor power and long-term management of reactor power. So this is a very brief review of chapter 5 that we have studied in our previous 3 weeks. And as I mentioned, I hope that related to figure 5.1, so I found that one student submitted his solution for this. Unfortunately, I have not checked that, but of course I will. And I also encourage other students to also challenge this problem and try to also draw a figure just like this. So with that, so if you are able to draw a graph just like this, then it can be said that you have pretty much sufficient understanding on this point kinetics, the theories of point kinetics. So I wonder whether we have any questions about chapter 5. Mm, well, So as I told you, usually this type of this simple, relatively simple sol solution and what is that? With all the assumptions applied to uh, to deriving this in our equation, and the solution is usually called as point kinetics. And I'm not sure whether we can find this word in our textbook. Hmm. And all we can see is here zero power kinetics. So by the word zero power, we usually ignore the amount of power generated or the amount of heat generated from the fission reactions, even if the number of neutron or even if the neutron density increases. And the basic assumption is that neutron density is so small, even if they significantly change, but the amount of heat generated from the reactor can be, or the effect of heat generated from fission reaction to the temperature of fuel and coolant can be somewhat ignored, or such a heat will not have a significant effect on the temperatures of fuel and coolant. And with that, zero power, so this is without feedback, is the case of zero power kinetics case. So it is a little bit early, but let me stop here. So why don't we have a short break from at this point, and then we are going to start section 7.6. So here, we did not cover section 7.6. So we are going to have a break until 4:20, and I would like to ask all the students to leave their names so that I can check the attendance of students. It was extended to 4 weeks, and then it is further now extended to 8 weeks, including the midterm exam. So that means today, so originally today is the last online lecture. I mean, it was planned that today would be the last online lecture, and next week we were planned to have a face-to-face lecture, but unfortunately, this online lecture will be extended for more weeks. So, and also this online lecture will include the time of midterm exam because it is extended to 8 weeks until the 8th week is finished. So let me also leave this announcement. So of course, most of you have already heard of this. It is so unfortunate, but this is just for protecting all of us, the health of all of us. So, and also according to the directions of the government. So, it is so unfortunate, but I would like to ask your understanding. Of course, you may understand that giving online lecture is much difficult to me. So anyway, and also I'm thinking about we can how midterm exam should be conducted. So of course, if it is decided, then I will let you know. But I would like to ask if you attend these online lectures and if you try to understand what is taught or what is mentioned in the courses in these lectures, then you will not have much difficulty, or that would be very helpful in not only understanding the contents of this textbook but also preparing the midterm exam. And I also want to remind you that I tried to show you some demonstration by using MATLAB. So if you also, if that was, because that was also given in the lecture, so maybe there can be a part, if you also have understanding on that, then that would be helpful in preparing the midterm exam. So that was unfortunate but necessary announcement about our lecture schedule. And now we are going to, instead of going directly to section 7.6, maybe so because we just finished chapter 5. We finished the chapter 5 and and also reviewed chapter 5, and in a very brief manner we are going to see chapter 6 and chapter 7 to have some connection with your knowledge with section 7.6. So chapter 6 basically deal with the spatial distribution of neutron density while ignoring the so-called temporal distribution of neutron density. So dependency of in chapter 6, in last semester we ignored this time dependency and only focus on their space and location dependency. So also we have neutron balance equation, and then we apply the diffusion approximation, so-called the fixed approximation, and we derived this equation, diffusion equation. So steady state diffusion equation, and applied this diffusion equation to different geometries. First, a plane geometry, and then uniform source geometry, plane geometry with a uniform source case, and we talked about boundary conditions, and then applied it to spherical geometry, and point to source example and two region example. So two region example was introduced to apply interface condition. And then diffusion approximation validity, and then 6.7 multiplying systems. From now on, the fission neutrons are introduced. So, you see, this would be, let me see, this would be the case of this would be the case of point source, and then critical reactor. So then we derived the neutron flux distribution as a function of distance from the source. And also the conditions for critical reactor was also mentioned. And in section chapter 7, we applied the diffusion equation to so uniform reactor. Basically, we applied the diffusion equation to cylindrical coordinate system. So before talking about that, let me first talk about equation 7.2 and 7.3. So this was the diffusion, basically the diffusion equation. So the first term with diffusion term, so the number of neutrons for a very tiny volume, usually denoted as dV, this would be the number of neutrons leaking out of that volume. So if it is the first term has the basically it is usually include leaking out, or it also this term may indicate the number of neutrons. How can I say, the number of neutrons that flows into the volume dV, depending on the depending on whether the net number of neutrons are positive or negative. If the net number of neutrons are positive, then neutrons are flowing into the volume. So anyway, the first term indicates whether, so on the surfaces, whether the number of neutrons are increasing or decreasing, or the number of neutrons are flowing into the volume or leak out of the volume. The second term, so by simply canceling nu in the numerator here and nu here, it is basically nu 0 multiplied with sigma f and phi. So nu 0 is so where can you find it? Nu 0 is the value for the case of, so nu 0 here is the number of neutrons per fission that would be required to make reactor configuration exactly critical. So nu 0 is the value for critical reactor. And so with this equation, nu 0, this 7.2 is the equation for critical reactor. So the reactor maintains its criticality. The effective value, the multiplication factor, is basically 1 in this case. And what if the multiplication factor is not 1? It is maybe bigger than 1 or smaller than 1. So in that case, so multiplication factor will be proportional to this value of nu. So we multiply 1 over k here. Then if we multiply 1 over k, then even if this k, the multiplication factor is not 1, and so basically if we delete this 1 over k, then that would not be 0. That means if the vector is not in a steady state condition, if the number of neutrons are gradually increasing or decreasing. So in such a case, the first term is the leakage term, this fission neutron term, and absorption term, and that will not be 0. So, but if we multiply 1 over k here, then it becomes 0. So that multiplication factor, this factor over 1 over k, the inverse of a multiplication factor, make this equation, the left-hand side, equals to 0. So after having this understanding, then 7.3 is for uniform vectors, and then finite cylindrical core. So cylindrical core, so the diffusion equation is applied to cylindrical coordinate system, and by separating variables, so neutron flux is now assumed to depend only on R and Z value. So for the distance from the center and the height from the bottom. And then eventually the result of solution, neutron flux, is given here. So some constant multiplied with J0 function, Bessel function, and so in radial direction we have dependency with Bessel function, and in G direction we have dependency with the cosine function. And C is a variable which can be determined by the reactor power, the magnitude of reactor power. And if reactor power is determined, then we are also able to determine this value of C, and neutron flux can be determined like that. And if we apply true group approximation, then after that, after all these procedures, and what we eventually get is that, so instead of L, we are able to introduce, instead of L squared, we are able to introduce M squared. So it is called M squared, it's called as migration area. And we may have some basic data for different types of nuclear reactors, such as the L1, L2, and M migration length. So L1 is basically fast diffusion length in fast energy region. L2 is the diffusion length for thermal region. And also we finished with the reflected reactors. So by placing the reflector here, then we may have some dependency. We may find the solution for this. And then we also talked about the reflector savings. And now we arrive at section 7.6, that is about control poisons. So Control poisons. What is control poisons? So control poisons are neutron observers that are deliberately included in the reactor pore. That is the neutron observers that are included intentionally with purposes. So they are control rows or soluble poisons such as boric acid that is included in pressurized water reactors. And also another form is something called the vulnerable poisons. They are usually embedded in fuel or other core constituents. They are included in the fuel. The name vulnerable comes from the fact that these poisons usually absorb neutrons in an early time period of a nuclear reactor. So early time period, like in the period of several months, while operating the reactor for 18 months. And then those poisons are burned, and then after some time period, like after 3 months, they do not have any effect as poisons because all the poisons were burned already. So these control poisons, like control rows or chemical shim, or soluble poisons, or these vulnerable poisons, they will have effect on the multiplication factor first. And if the distribution of such control poisons are not uniform in the reactor, like the case of control rows, then that might affect the distribution of neutron flux. So to analyze this, we are going to or inserting control rows into the reactor will basically increase the absorption cross-section. So that increased macroscopic absorption cross-section is designated as delta sigma A. So that's the amount of increased absorption cross-section. So with this, that increased, or this would be, so sigma A would be original absorption cross-section, and delta sigma A would be, of course, the amount of added absorption cross-section due to control rows. Or it can be also interpreted that the sigma, so this is if the sigma A is included by control rows, that would be the amount of absorption cross-section included by control rows. That's what delta sigma A would be. So how can we analyze that? So I think it will not be very difficult for you to follow this step by step. So first, the basic assumptions are K. So initially, the reactor was in a steady state condition. So before inserting reactivity, the multiplication factor, and phi is denoted as K and phi. And after inserting the neutron poison, or after inserting the control rows, then the multiplication factor and neutron flux is given or is denoted as K prime and phi prime. So in that case, so let's try one by one. So in fact, we are in chapter 7 and section 7.6. So let's first write what equation 7.3 tells us. So in a steady state condition, then where is gradient? And here. So Laplacian and phi. So I first, this is the equation before inserting the reactivity or before inserting the neutron poison. And the second term would be, in fact, 1 over k, and it is highly likely that k equals 1. And basically nu would be the average number of neutrons produced, and sigma f S and sigma f and phi and minus sigma a and phi. It becomes 0. So this would be the diffusion equation before providing the negative reactivity. And after inserting negative reactivity, or after inserting the neutron poison, then first what you should recognize is that we are going to assume that the diffusion coefficient will not be significantly affected by the insertion of control poisons. So after inserting neutron poisons, this would phi prime is the neutron distribution after providing neutron poisons. And multiplication factor will change. And then, of course, the neutron flux after that. And absorption cross-section will change. From this original value, then some small amount of sigma A that is the increased absorption cross-section by neutron Poisson, like by inserting control rods. So this is equation 7.72. And what happens after that is that, oh, I'm sorry. What happens is that we are going to multiply phi to each term. So by multiplying, so in this case, we are going to multiply phi prime. Of course, phi prime will be also a function of location. And phi will be also function of location. So to be more specific, these are all functions of location. And in the first equation, we multiply phi prime to each term. And phi prime. And in the second equation, we are going to multiply phi to each term. And then these are the equations for very small, tiny volume dV. So if these equations are satisfied, then after integrating over all volume, the equation will also be satisfied after integrating. If integration is performed for all the volumes. So dV, and also integration dV. And the same integration should be performed here. dV and also integration is performed for this. So, and then we are going to subtract the first one from the second one, or vice versa. So we are going to subtract one with the other. Then we are going to have just one equation. So to make this consistent with our textbook, we are going to subtract from the first equation from the second equation. So in that case, what will be remaining is that this minus the term here. And in the second case, so of course here, maybe to make the notation much simpler, here we are going to delete this indication that phi and phi prime are functions of location. They are. I just delete this to simplify, not simplify, to make the form of equation simple. Of course, these are still the functions of location. Phi, phi prime, they are all functions of location. So we should keep in mind that even if we delete this parenthesis and R vector. What about the second one? Of course, similarly. So here we have, inside of integration, we have a phi prime, and we have the same new sigma f and phi. And phi prime will be same with phi prime and phi. So, in other words, this minus, basically this minus 1. Subtract this. Of course, also for simplicity, we are going to delete R. But phi and oh, I'm sorry, I copied out wrong one. This one. It should be and delete. And phi multiplied with the phi prime is basically the same with this phi prime. So we may take this part out of the parenthesis, and this would be what will be remaining. And also, the last term would be, so we still have the same phi and phi prime, However, in the second term, we have sigma A and delta sigma A. In the first term, we only have sigma A. So this would be what will be remaining. So from now on, now, interesting part is that the first term, will become 0. So for that, maybe you are able to see these equations. So if we first think about divergence of phi and the gradient of phi prime, and also if we think about divergence of phi prime and gradient of phi, then, so because this is divergence, the first one would be phi n, the second one would become the Laplacian, and also plus gradient of phi multiplied with gradient of phi prime. Even if we change the order phi prime gradient of phi, in this case we are going to have a phi prime Laplacian phi plus the second term will be same. So if we subtract the second one from the first one, so that means equation 7.76 minus 7.77, then the left-hand side will become this one. This would be the left, I'm sorry. That would be this part will be same with the first term on the right hand side minus the first term on the right hand side in the two equations. So, and the intention was that we wanted to calculate this part. And this would be same with the divergence of the first one minus divergence of the second one. So in other words, the divergence of phi gradient of phi prime minus phi prime gradient of phi. So the minus of the left-hand side. And by applying divergence theorem, so divergence of the volume, divergence of the integration over divergence of all the volume will be same with the total amount of, so here by divergence it tries to calculate the total amount of leakage in all the volume. That will be same. So instead of counting all the leakages of the volumes inside of the volume of interest, maybe we may do the same calculation by calculating all the number of leakage in the total volume. So in calculating the leakage in the total volume can be performed by dA would be the small volume in the surface, and n vector would be the normal vector for the volume. So the second term, this one, will give us the total amount of leakage in the volume V. So this is basically the divergence theorem. So divergence of the volume will be same with the integral over all the surface, the number of things that is leaked out of the volume. And in that case, this would be 0 because, so if we consider this function, then in the surface of the reactor, phi will be almost 0. Phi will approach to 0 due to the boundary condition. And also phi prime will approach 0 due to the boundary condition. Let me find it in our textbook. So 147. So if we think about the boundary condition, then the neutron flux in the surface, in the boundary, the neutron flux will gradually decrease and eventually, not exactly 0, but eventually becomes 0 for this after some extrapolated distance. And if the extrapolation distance is very small compared to the size of the reactor, then we may approximate that in the boundary, neutron flux becomes 0. And the integration that I just showed you is the integration for this surface. So in that surface area, we need to know the amount of absorption cross-section inserted into the reactor. And that would be denoted as the absorption cross-section of control rod. So of course this C will indicate the control rod. So for this area, that would be the amount of absorption cross-section, additional absorption cross-section inserted into the reactor. In other parts of the reactor, the inserted control rods, inserted absorption cross-section will be 0. So with that in mind, and also by using some assumptions like we are not going to dependency on azimuthal angle omega, and then another one is that the cross-section area of the rod is so small, then their variation, the R variation, will not be significantly different. That means this cross-sectional area is so small, then we don't need to consider the difference between the R, the neutron flux in this point and after, and R plus the diameter of a control rod. So the integration. So the interesting thing is that we should deal with phi squared. So this would be the cross-sectional area of the control rod here, and sigma AC would be macroscopic cross-section of the control rod, and the integration should be performed. Integration should be performed from h over 2. That is because the height. This is the point of h over 2.